Okay, so this is the pre-class lecture for Wednesday, November 7th, and it picks up where I left off in class this morning, talking about the idea that an E2 reaction has to go through this anti-periplanar transition state. So when the base comes in and removes the beta hydrogen, the pair of electrons moves here and the leaving group leaves. The orientation of the hydrogen and the leaving group have to be anti-periplanar, which means that the hydrogen and the leaving group have to be anti to each other. And if they're anti to each other, then technically they're periplanar. And the reason for this had to deal with the idea that we want to have as minimal number of moves as possible in going from the reactant to the product. So if we write out the sp3 hybrid orbitals for this molecule, so I've got my sigma bond, I've got my two sp3 hybrid orbitals, one bonded to the beta hydrogen and one bonded to the leaving group, then the idea here is that these, as the hydrogen is pulled off and as the leaving group leaves, what will happen is that we'll go through a transition state where the two sp3 hybrid orbitals will sort of become in between sp3 and sp2 hybrid orbitals. So they'll kind of swing like this. They'll kind of swing up in both cases until they finally form two p orbitals, where the p orbital on the left has two electrons because that hydrogen has been removed by the base. And of course, the p orbital on the right has no electrons in it, so that now these two can overlap to form the pi bond. So the idea is that these two orbitals have to be parallel to each other in order to go from being sp3 in one smooth motion to the p orbitals. And they also have to have the large lobes on opposite sides of what will become the double bond, because that's the way the orbitals are going to grow. So what that means is the hydrogen and the leaving group have to be anti to each other. And at the end of class, in either the 8 or the 9 class, I then applied that to say, okay, if you had this molecule with two different beta hydrogens, HA and HB, which one of these hydrogens would be removed by, let's say, a Tert-Butoxide ion in this cyclohexane ring? And it's the cyclohexane rings that are going to play an important role here in terms of the anti-periplanar geometry either being able to be formed or not. So the question is, can the Tert-Butoxide remove HA only, HB only, both of them, or none of them? And your gut instinct tells you that if this has to be anti, then at least my gut tells me that the hydrogen and the chlorine should be trans to each other in order to be anti. And that's exactly what will happen. So when we look at the leaving group, only those hydrogens that are trans to the leaving group can be removed by the base in an E2 mechanism. So let me rewrite this structure and I'll show you exactly why that's the case. So if my chlorine is above the plane of the ring and my hydrogen is then below the plane of the ring, then it can be removed with a base. So if I bring in my Tert-Butoxide, it can remove HA, this pair of electrons moves here, the chlorine gets kicked out, so that I can form the double bond here. So the idea is that the hydrogen, the beta hydrogen, must be trans to the leaving group in cycloalkanes for it to be removed in E2. Okay, so only the beta hydrogens that are trans are going to be those that can be deprotonated by the base in an E2 mechanism. Now, why is that the case? Well, let's look at a chair conformation here. The chair conformation, if one carbon is the alpha carbon, then that means the beta carbon is next to it. So I'm looking at 1,2 disubstitution. Now, ideally, if my chlorine is going to be, if I put my chlorine here, where does the hydrogen over here on the beta carbon need to go to form that anti-periplanar geometry? If you said it has to go in the axial position, you're correct. So maybe here's R1 and R2, two different alkyl groups. So this is actually the geometry that is going to give me the anti-periplanar geometry. The hydrogen and the chlorine being anti. And you might say, well, okay, so that means that the hydrogen and the chlorine are trans to each other. And that's exactly what I've said over here. Now you might say, but what happens if the hydrogen and the chlorine are, let's say, in this conformation? Can they undergo E2 elimination in this case? And the answer is no, because they're not anti-periplanar. But what has to happen then? What has to happen is you have to do a ring flip in order to then interchange the H and the Cl groups. So now, actually, that's not the correct. The way I have it drawn here, it would be this Cl goes there, and then the R2 goes here, and then that hydrogen goes there, and the R1 goes there. So this molecule would undergo a ring flip, and now the HCl is anti-periplanar to itself. If the H and the Cl are cis, and I'll draw that structure out here, if you have the H and the Cl cis, there's no way that this hydrogen and this chlorine can ever become anti. Okay, so we'll never have a conformation where H and the Cl become anti if the H and the Cl are cis. Okay, so there's just no way to twist this molecule around to put the hydrogen and the chloride anti. You can only have the anti-conformation occur if the H and the Cl are trans to each other. Okay, and so that's the reason why we have the rule that says it only E2 in E2 reactions, only hydrogens that are trans to the leaving group can be removed. Okay, so let's take an example here. Let's look at another example. And this is actually the real example that I used this morning in the 8 o'clock class. Okay. If I was to react this with NH2 minus, which means that the reaction is automatically E2, because it will automatically be an E2 reaction if it's NH2 minus or Tert-Butoxide. Which hydrogen could be removed? Which of the beta hydrogens, HA or HB? Both or neither? If you said they both could be removed, then you're correct. So we could have the NH2 minus come over, remove the hydrogen, have the pair of electrons move there, kick off the bromine or chlorine. So one of the products that could be formed is sorry. Got to get our bonds in the right positions here. How about this? That looks better. So then I would have, this is my first possible product. Or the other possible product is that the NH2 minus can come in, grab this hydrogen, have that pair of electrons move here, still kick off the chlorine. So the other possible product would have the double bond here with then HA and the CH3 group there. And so this is how people proved that the anti-periplanar geometry was necessary for E2. They had a series of different molecules undergo reaction, and every time they saw that the beta hydrogen had to be trans to the leaving group. Okay, so that's the rule for cycloalkanes. The leaving group must be trans to the hydrogen in order to have that hydrogen be removed in an E2 elimination. Okay, so let me give you another problem here, and you can see, can you write the major product of the following reaction? Or the major products of this reaction. What am I going to do here? And I'll put the hydrogen here, and I'll put the CH3 group there. Okay, so how many unique products are there if we use NH2 minus? So can you write all of the possible products that can form when this E2 reaction occurs between NH2 minus and this molecule? And then can you circle the major product of this reaction? Okay, so two things I want. I want you to write all the possible products and then tell me what's the major product for this reaction. Now, if you're overly ambitious, or if you're not so overly ambitious, stop right now, write the answer, and then turn the tape back on and I'll show you if you're right or not. How many beta hydrogens do we have in this system? Well, here's a beta hydrogen. Here's a beta hydrogen. And then it turns out that these are beta hydrogens as well on that CH3. So if I write the molecule down here with HA, my Cl, my CH2 with the H on it, so we'll call that HC, and then down here, HB and CH3, how many of these hydrogens are going to be able to become anti-periplanar to the chlorine? Well, HA is trans to the chlorine. HB is not. It's cis to chlorine, so it could not be removed. How about HC? Well, since there's 3 hydrogens here, we have freedom of rotation, and so in this case, any of the HC hydrogens could be removed. So that means I could get two possible products. I could have my NH2 minus come in, grab that hydrogen, have that pair of electrons move there, kick off the chlorine, and so I could get product A here, which would have the double bond here. So there's product A. Or, let me change pen color here. I could have the NH2 minus come down here, grab HC, pair of electrons moves there, chlorine gets kicked out, so that product C would have the double bond outside of the ring to the CH2. And this would be product C. Now, there is no product B because B is cis to the chlorine, so it cannot be removed by the base. Now, I've written the two possible products, product A and product C. Which one is the major product? For this reaction with NH2 minus, which one is the major product? If you said A, you're correct, because I'm using a small sterically hindered base, and so A turns out to be the most substituted, therefore the most stable product, and that's what's favored by NH2 minus being used as the base. If I wrote this problem with Tert-Butoxide, so if I came over here and said I'm going to react this with tertiary butoxide ion, the first criteria is that only hydrogens that can become antiperiplanar to the chlorine are going to be deprotonated. That means HA and HC as I saw earlier. HB being cis to the leaving group could not be deprotonated in E2. So I would get those same two products that I just wrote. One, my double bond here, which I called product A before, and the molecule with the double bond outside the ring, what I call product C because of the fact that I labeled the beta hydrogens outside the ring as C. So now if I change the base and I do this reaction under Tert-Butoxide, a sterically hindered strong base, what would be the major product of this reaction? Well, given the choice between HC and deprotonating HB, HB is a tertiary hydrogen, HC is a primary hydrogen, therefore it's less sterically hindered. And so therefore product C would be the major product of that reaction. So when you're doing E2 eliminations on cyclic systems, I have to tell you the stereochemistry so that you can make sure that your hydrogen can become antiperiplanar to the leaving group. When I do that, then you have to only write the possible products where the beta hydrogens can become antiperiplanar. If they can't, then you're not going to get an E2 reaction. Then, after writing those possible products, you have to look at the base that we used. If we use the small NH2 minus base, we're going to get formation of the most substituted alkene, the so-called Zaitsev product. And if the base is Tert-Butoxide, then I'm going to remove the hydrogen from the least sterically hindered beta hydrogen, which will give me the least stable molecule because the double bond will have the least number of alkyl groups attached to it. Okay. So that's how we look at the stereochemistry of the E2 and the antiperiplanar geometry. Okay. Now, the last thing I want to do, well, there's two last things I want to do, if that's even possible, is to now modify our SN1, SN2, E1, and E2 chart. You may say, well, wait, we didn't have all four of them together. I know. So let's start with the chart that we had. We had alkyl halide, we had strong nucleophile, we had weak nucleophile, and then we had primary halide, secondary halide, tertiary halide. And so what we said was that a primary halide with a strong nucleophile underwent SN2. With a weak nucleophile, there was no reaction. Secondary halide plus strong nucleophile was again SN2. Secondary plus a weak nucleophiles only undergo SN1, so we have SN1. But now, given our conversation of last week and this morning, we now see that SN1 has the same first step as E1, so whenever we do an SN1 reaction, I'm always going to get a little bit of E1 products. So I'm going to get SN1 and E1. Now for tertiaries, tertiary halides also can only undergo SN1. So before we had SN1 for both of these reactions, and now what I'm going to again say is that when you get SN1, you're going to get a little E1 products. So this is our new modified table for predicting the mechanism given a primary, secondary, and tertiary halide with a strong nucleophile or a weak nucleophile. Now I can add a third column to this and say, what about strong base? And my strong bases are going to be limited to NH2 minus or Tert-Butoxide. And in each of these cases, the mechanism is going to be E2. So whenever we do a reaction with NH2 minus or Tert-Butoxide, that mechanism is automatically going to become E2. You're going to get the more substituted alkene with the NH2 minus, the small base. You're going to get the hydrogen that is least sterically hindered removed by the Tert-Butoxide. And we also have the final thing that the hydrogen that is being removed has to be antiperiplanar to the leaving group. Okay, so there's our new table of predicting whether it's SN1, SN2, E1, or E2. And it's relatively straightforward. You just have to think about what am I using, nucleophile or base, and then the corresponding mechanism, whether it's from a primary, secondary, or tertiary Remember, primaries can only undergo SN2, tertiaries can only undergo SN1. Okay, so that's almost the end of SN1, SN2, E1, and E2, except that I gave you problems last week. Can't remember if I gave you any for the test. Probably not, but that's okay. There's a third test coming, where I said, let's take something like let's take tertiary-butyl chloride, tertiary-butyl bromide, and let's react these with something like hydroxide. Now I'm going to have to make that more of a plus looking. And I said, which one of these reactions goes faster, or do they go at the same rate? The first step in this is to identify the mechanism of the reaction. Well, in this case, these are both SN1 reactions. Now, what's different about them? The difference is in the leaving group. Does the leaving group play a role in the rate of reaction? Leaving group plays a role in every single one of these reactions, whether it's SN1, SN2, E1, or E2, since it's part of the rate determining step of any of those reactions. So looking at this mechanism, we would say, okay, bromine is the better leaving group, and so therefore the bottom reaction would be faster simply because a better leaving group is going to cause it faster, SN1, SN2, E1, or E2. Now what I'd like to do for the final topic is to talk about how solvent can play a role. And in order to talk about that, I need to define a couple of solvents. Okay. Can a solvent make an SN1 or an SN2 reaction go faster? And that's all I'm going to limit the solvent's role to, is in SN1 or SN2. Okay. And so what's its role in determining the rates of these two reactions? Well, there's two types of solvents. There are what most textbooks call protic solvents, and there are those that they call aprotic. Now, I don't like those terms, and I'm going to redefine them here in a minute. But when we're doing SN1 and SN2 reactions, we're normally reacting a negatively charged nucleophile, or we're getting a negatively charged leaving group leaving, or we're getting a carbocation intermediate being formed, or we're forming a transition state that has charges. And so overall, the types of solvents that I'm talking about for doing SN1 and SN2 reactions have to be polar solvents. We can't run an SN1 or an SN2 reaction in a nonpolar solvent because we have all these charged species that need polar solvents to dissolve in. Okay, so when I talk about the rates of SN1, SN2 reaction as it relates to solvents, I automatically am talking about two classes of polar solvents. Those that are aprotic and ones that are protic. Now, I like the terms, instead of protic, I like the terms hydroxylic and non-hydroxylic. I'm kind of old school in that terminology, which that terminology actually had been was around when I was doing my PhD thesis. So I like hydroxylic and non-hydroxylic, but most textbooks like protic and aprotic. Well, what does that mean? Well, let's look at some different types of polar solvents and put them into these two classifications. So what kinds of hydroxylic polar solvents do we have? Can you think of any? Well, I can. I can think of H2O. I can think of alcohols. That's pretty much it. Can I think of some aprotic polar solvents that are non-hydroxylic? Well, probably the one that we've encountered the most this semester in lab has been this one, which is acetone. There are also molecules like this, a C triple bond N. This is called acetonitrile. There's also one with a sulfur. And this one's called dimethyl sulfoxide, which is also abbreviated as DMSO. And DMSO is a kind of a weird solvent in the fact that we don't use it in the lab because if it gets on your skin, it goes straight into your bloodstream. And so we kind of have to treat it with a little bit of respect. So acetone, acetonitrile, DMSO, these are examples of polar solvents that don't have OH groups, and so they're considered to be non-hydroxylic. Now, given these two classes of polar solvents, do they play any role on the rate of an SN1 or an SN2 reaction? Well, let's start with what role they would play in SN1. So can you write the rate determining step for an SN1 mechanism? Well, I can. And my rate determining step of SN1 is the formation of the carbocation. That's my rate determining step. Now, if we look at this reaction, I have C plus species over here, and then I have the leaving group as also a charged species. And so what we look at here is that the solvent that will speed up this reaction is the solvent that does better solvation of the products. So if you have a solvent that will solvate the products better than another one, that will speed up the formation of the carbocation. Okay, so does that make intuitive sense? That when I have better solvation of my ionic products, I'm going to get a faster SN1. Well, yeah, because that's the rate determining step. So which sets of these solvents, protic or aprotic or hydroxylic or non-hydroxylic, which one of those solvent pairs actually solvates cations and anions the best? Well, it turns out that the ones that can solvate the best are your water or your alcohol, where the delta minus oxygen can interact with the C plus, and by the other way, the delta plus hydrogen on the water can interact with that halogen leaving group. So it turns out that alcohols and water, this would also be true for an alcohol if I wrote its structure like this. These two solvate ions the best. And so down here in the SN1 mechanism, these two cause SN1 reactions to increase in rate. Okay, so the hydroxylic solvents are the best at speeding up SN1 and SN2 reactions because they solvate the products the best. They make the products more stable, pushing the reaction towards the formation of the products. What happens in SN2 then? In SN2, you have a nucleophile that's coming in to attack the carbon to kick off the leaving group. Which solvent speeds that reaction up? Well, here's what we have to remember. That if you had hydroxyl groups coordinated to your nucleophile, these hydroxyl groups, these hydroxyl solvents, are actually going to slow down the attack of the Nu- on the C in SN2. Okay. So while SN1 reactions get speeded up because those solvents solvate the negatively charged anions better, like the leaving group, in this case they're going to slow down the attack of the nucleophile on the carbon. The nucleophile is going to have to get rid of all its solvent molecules before it can go into the transition state. So if hydroxylic solvents slow down SN2, what speeds them up? Well, SN2 reactions are speeded up by non-hydroxylic solvents. And why non-hydroxylic solvents? Because they're going to be not as bound as tightly to the nucleophile as the hydroxylic solvents, and so therefore the non-hydroxylic solvents all speed up SN2 because of their weaker solvation on the nucleophile. Okay, so when we look at solvents, SN1, you get an increased rate by using alcohol or water. And for SN2, you increase the rate that rate by using the non-hydroxylic solvents. Okay. So that's how solvent plays a role in SN1 and SN2 reactions speeding up. You may say, well, what role does solvent play in E1 and E2? Well, solvent would play the same role in E1 as it does in SN1, since E1 and SN1 share the same first rate determining step. The idea of looking at solvent effects on using strong bases like E2 isn't something that we're going to get into, because it turns out that if your base is strong, it could deprotonate either water or your alcohol. And if the base is really, really strong, it will react with your non-hydroxylic solvents. And so all I'm going to ask is for the effect of solvent on SN1 and SN2 reactions. Okay. So that's the end of the SN1, SN2 reaction mechanisms. Here's our chart that shows us how to predict SN1, SN2, E1, E2 reactions. And then that allows us to write our products. And we know how nucleophilicity, leaving group ability, and now solvent play a role in speeding up SN1 versus not speeding it up. And the final thing we talked about was the idea that when we do E2, small bases will give us the most stable product, Large sterically hindered bases will give us, in general, the least stable product because those are the most accessibly available hydrogens for those types of things. And when we determine then, when we look at cyclic systems, we have to have our E2 reaction go through an anti-periplanar geometry. And so in a ring system, that means that the beta hydrogen must be trans to the leaving group in order for an E2 mechanism to occur. Okay, so that's the end of SN1, SN2 for the moment. In Chapter 7, we're going to get into a little bit more and start using different leaving groups. But for the moment, this is the combination of all four of the mechanisms. So what we'll do in class on Wednesday is we'll go over some of these reactions. I will try and put some E2 homework problems online this evening, although I don't know that that's going to happen. But probably on Tuesday I'll put some more homework problems, or I'll put some homework problems up dealing with writing the mechanisms of E2. For Wednesday's class, there won't be an in-class quiz, but I'm going to try and whip up a short online quiz here in a minute that should be available before Tuesday morning. Okay, so that on Wednesday we'll finish up talking about SN1, SN2, E1, E2, and I'll ask you to be able to identify the mechanism as well as write the major products of E2s and E1s and of the SN1 and the SN2 reactions.